All right, so here's the deal. All of the problems on the 8.3 worksheets were conservation of energy problems. So those were problems where your total energy was constant. So you could look at any point in the motion of the object and your total energy wouldn't change. All right, and the physicsy reason for that is because there's no work done by non-conservative forces. All right, in simple terms, it basically meant that friction wasn't causing you to lose any energy in any way, and nobody like Roy or anybody was pushing on the object, sort of adding any extra energy into the system. Okay? So now the question becomes, well, what happens if there is friction that causes you to lose energy? Or what if Roy comes along and pushes the object and gives the object more energy? Okay? In other words, what if there are non-conservative forces doing work? Okay? So we're going to talk today about how to solve those problems. So there we go. Let's do this. All right. So let me embiggen this. You out of my way. You next page. Okay, cool. So you've seen this before, but just as a quick reminder, in sort of a, I keep using this word holistic. In this holistic sense, conservation of energy says that the amount of energy we got in the universe is a constant. Okay. What that means for us is, as long as energy doesn't get transferred from one object to another, then the total energy is constant. And that's what's been happening. Okay? Now we're going to start talking about what happens when energy gets transferred from one object to another. Okay? In other words, if Roy exerts a force on an object, then he's burning the chemical potential energy from the Cocoa Puffs he had for breakfast and giving that chemical potential energy to an object. Okay? Maybe he's pushing a lawnmower or lifting a box or whatever. So you're literally transferring energy from Roy to the object. Okay? Similarly, when friction stops an object, so in the lab that's labeled as thermal energy, right? Okay? If you rub your hands together, your hands get warm, right? Okay? And what you're doing there is you're causing the molecules in your hand to vibrate faster. And you guys know that when you heat stuff, the molecules vibrate faster, right? So technically, thermal energy is just the kinetic energy of the little particles that make up your object. Okay? But so, long story short, when a car jams on the brakes and skids to a stop, some of the energy gets transferred to the earth itself, because you're pushing the earth, okay? And some of it becomes heat because of the friction between the tires and the road. Follow? Okay. So, I guess that's what I need to tell you here. So, okay, so these equations here are going to come up again today. Really, the main one that you need to understand is this. All of the problems that we've done so far have had no work done by non-conservative forces, right? And as a result, our change in total energy has been zero, right? So really, this equation is going to be the one that's the most important to us. All right? This one almost never becomes an issue. Basically, this is just saying that the work done by gravity, for example, is your change in potential energy. So when you drop an object, you lose potential energy but gain kinetic energy. And that's what gravity is doing. Okay? Now, in the same way that net force causes an object to accelerate and changes velocity, it turns out that if you calculate the net work, you find the total of all the works by all the forces, gravity, friction, everything, because net force causes acceleration, net work causes a change in velocity, a change in kinetic energy. Okay? So that's sort of a quick overview, but ultimately this is the equation that we're going to end up using the most as we do these work problems. Cool? All right, great. So that's sort of a quick overview. That was a horrible noise. Sorry about that. All right, so then the question is, how do we do work? How do we transfer energy from one object to another? So that's what we're going to talk about. All right, so probably the easiest way to do this is just by doing a few examples. Okay? So in this one, it says Roy lifts a 5-kilogram box of papers from the top of a desk that's 0.8 meters tall, and he places it onto a shelf that's 1.5 meters above the floor. And we're going to figure out how much work he did. Okay? So the premise behind this is the following. While he's lifting the box, there are going to be two forces on the box. Specifically, gravity is pulling the box down, and Roy is lifting the box upwards, right? Cool. So what's our only non-conservative force here, you guys? Roy, right? So what I just finished explaining was this, that I know that the work done by non-conservative forces is equal to my change in total energy. Well, again, I know you just answered this, but what's the only non-conservative force? Roy. So that means that the work that Roy did, the work that Roy does is our change in total energy. Because he's the only non-conservative force. Follow? All right, so in the last section, one of the things that I hope I impressed upon you is the importance of thinking in terms of height and velocity at different points in the object's motion. Okay? That's still going to hold true here. All right? Check it out. We've got our object. Roy is lifting it. So, out of my way. Foxy. Okay, so here's the table, here's the shelf. Here's the box. We're going to lift it from here to up onto the shelf. Cool? So, table, box, okay. All right, so we want to think in terms of height and velocity. So presumably, down here, when the box is sitting on the table, what's the velocity? 0. Oh, well that means that the kinetic energy here is going to be 0, right? Okay. Now it tells us the height of the table. It tells us the height is 0.8 meters. So what should I use that information to calculate? Gravitational potential energy, right? So if you do that, it turns out that the GPE, the gravitational potential energy, is 39.2 joules. Is everybody okay with how I found that or no? Just NaGH, right? We know our mass, acceleration of gravity is 9.8, and we know the height. Good? Abby, okay? You sure? Everybody good? Okay, cool. So I can find my total energy. This is the total energy that the box has initially. 39.2 joules, right? Now, if Roy didn't touch the box, that would stay constant, wouldn't it? Okay, but then there's this non-conservative force from Roy exerting force on it. So then when the box gets up to here, now it's at a height of, what does it say, 1.5 meters, right? So what should I do? Calculate the new GPE, right? So the new GPE is going to be NaGH. It gives you 73.5 joules. Good? All right, and then it doesn't say it explicitly, but it says he places it onto a shelf. So what should we assume the velocity is? 0, which means that our kinetic energy now is 0, which means our total energy is now bigger than it was before. Follow? So that's my TE final. All right. So now we can find the work, right? Because the work that Roy did, because he's our only non-conservative force, the work done is the change in total energy. So what am I going to do yet? Just subtract, right? So here we go. Let's see. So the work done by Roy is the work done by non-conservative forces. That's TE final minus TE initial. Please remember, you guys, anytime you do change, it's always final minus initial. It's going to be really important in this section. So for us, it's, well, let's see, we ended up with 73.5 joules. We began with 39.2 joules. And so the work is 34.3 joules. Questions with what we did there? Okay, so what does that number mean? Basically what I want you guys to be thinking of is this. Work done by non-conservative force, and I will usually just say work because I get sloppy, but the work done by non-conservative force is the change in total energy. We started out with this much energy, we gained this much energy, which is how I want you to think of this, and so we ended up with this much energy. Okay? So the work done by non-conservative forces represents how much energy you gain or lose. What would be different if we'd lost energy, you guys? Okay, you would be lowering it maybe. How would it change? How would this number look different if we had lost energy? It'd be negative. Good. So positive work implies an increase in energy. Negative work implies a decrease in energy. Okay. Also, remember, point for me. Which way did Roy push the box? Up. Which way did the box move? Up. Positive work, because they're working with each other, right? When he lowers it, he's pushing up, but the motion is down. So that's negative work, right? Which makes sense because he'd be losing GPE. Cool? Questions with this? All right, cool. So this is what work is. So in simple terms, this is a little bit oversimplified, but work is the change in energy. All right, so if you wanted to kind of summarize, that's the deal. That's what work is, change in energy. For us, we're going to focus on the change in total energy. All right? But I still haven't talked about how you find, like, how you do work. Okay? So you have to have a non-conservative force and you have to have motion. So it seems like there should be some connection there between how much force I'm exerting and how far the object moves and how much work is done. Okay? So that is this slide. All right? So the idea is work is going to be done by a force. All right? So if you want to calculate the work done by a specific force, here's the equation for it. To find the work, you take however much force is being exerted, you multiply it by the distance that it moved, times the cosine of the angle between them. As a quick comment, remember I told you guys that the force couldn't be perpendicular to the motion? What's the cosine of 90? 0, right? The cosine of 90 is 0. So notice, if you put 90 in here, you're going to get a work of 0, right? Cool? All right. Also notice, if I push it this way, but it moves that way, what's the angle between these two vectors? 180, right? What's the cosine of 180? Close. -1. -1, right? So notice, if your angle is 180, that's implying that your force and your distance are opposite each other, and it gives you negative work. Follow? All right? Now, just like when we did torque, you remember how usually the angle was 90 degrees, right, for most problems, and then occasionally I threw a problem in where it was like, ooh, this force is at a weird angle. Same thing's going to apply here. Usually, this angle will be either 0 or 180, okay? But occasionally it'll be the weird angle. So anyway, here's explanations of what all the things are. W here is the work done by a given force. F is how big the force is. D is the displacement, how far the object moves. Theta is the angle between those two vectors. Shoot. This second bullet here, or this second to last bullet here, where it says F is the magnitude of the force in the direction of displacement, that's supposed to be this, F parallel. So I put F parallel here. I'll explain that in the next example. Okay? And then similarly, this is supposed to say D parallel. And I'll explain that when we do the example. Okay, so that's kind of the deal. So let's do this. I think there's a lawnmower example or a box example on the next page. Box. Okay. Everybody good with this? I think, again, probably the easiest way to get it is just by doing an example. All right. So here we go. All right. So we got a box with a mass of 40 kilograms. It's pushed from rest 12 meters across a horizontal frictionless floor with a force of 50 newtons exerted at an angle of 30 degrees below the horizontal. Find the final velocity of the box. And the answer's there in parentheses. All right. Please, 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 super please, make a drawing. Okay. Identify the important points in the object's motion. And just like last section, you need to be thinking in terms of height and velocity. Okay? You've got to be thinking in terms of height and velocity. So here's my drawing. Here's the floor, horizontal floor. Here's the box. It starts here. It says it's pushed from rest. So the velocity here is 0. And then I'm going to push it a displacement or a distance of 12 meters. We're going to get a little sloppy about the difference between distance and displacement here because it ends up not being really an issue. All right, and the question wants to know what's the velocity here. Let's see, what else do we know? We know that the mass is 40 kilograms. And I know that my force is 50 newtons at an angle of 30 degrees. So let's draw that in red. I'm going to draw that arrow pointing in, even though I spent a whole bunch of time telling you not to do that. 50 newtons, and then this angle here, 30 degrees. All right, is everybody good with this? Any problems? All right, now, the thing I stressed when I started this was I said you want to be thinking in terms of height and velocity. I wrote down some information about velocity. What about height though, you guys? Yeah, it's always going to be 0, so I mean, just make a little note. Oh, my, oops, that's black. Oh, seriously? So the height here is 0, the height here is 0. Cool. All right, so the idea is there's going to be a net force on this, right? It's frictionless, which makes things nice. So there's going to be a net force that's going to cause it to accelerate. Because it accelerates, it's going to gain velocity, blah, 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 right? Okay, so we certainly know enough to solve this without using energy, right? I mean, you could find your net force, find your acceleration, and then use one of the kinematics equation and find the final velocity. And that would work. But I want you guys to try to use energy concepts, okay? So, let's do this. I guess let's establish this. What's the total energy going to be at this first point, you guys? 0, right? Because we got no velocity, so there's no kinetic energy. We got no height, so there's no GPE, right? So the total energy at the beginning is 0. Now, is the total energy going to be constant? No, because we've got a non-conservative force, specifically the force of Roy, right? All right, now let me talk for a minute about that, the cosine theta in the equation. All right, Roy's force has 2 components to it, doesn't it? I don't know if you need to draw this, maybe just listen for a minute. I'll draw it in green. So this force has 2 components, right? There's a force of Roy vertically pushing down. Is that force going to do any work? No, because the box is moving this way, and the vertical component is perpendicular to the motion, right? In other words, that's not going to affect the velocity of the box at all, is it? Not directly, anyway. Good? The component that's going to affect the velocity is the horizontal component, the x component, okay? I would have called that the parallel component, as in it's parallel to the displacement. So that's what this F parallel means, right? Because in this problem, the x component is parallel to the motion. Follow? Okay. So we can certainly find that, and to do that, it would just be 50 times the cosine of 30, right? Make sense? So that's where the cosine 30 comes from. It's finding the component of the force that's parallel to the motion. Cool?
It's always going to be that for every problem.
You need to, just like with the torque section, you had to make sure that the angle that's given is the angle between the force and the lever arm. This time you got to make sure that the angle that's given is the angle between the force and the displacement. Which this time it is, because the angle is 30 degrees off the horizontal and the motion is horizontal. Follow?
Yeah.
Good question. All right, is everybody good? All right, so I can find the work, right? So work is F d sine theta. So my force is 50 newtons. The distance the box is moving is 12 meters. Oh, shoot, I put sine. It's not supposed to be sine, sorry. Have it. Cosine, sorry about that. Times the cosine of 30 degrees. So multiply that all out, and it gives you a number that I've written on this piece of paper. Gives you like 519.6. And notice the units do turn out to be joules, right? You get Newton meters, which is what we said a joule was. All right, everybody good? All right. Evan, you doing okay? You following along? This is not easy, so make sure you guys are following along. Great. So great. So what does that number mean? We did 519 joules of work. What's it mean? What do you got? In this example, yes. In general, no. So the work isn't equal to the total final energy. The work is equal to the change in total energy. But you're right, this time because you start at 0, the change is equal to the final. Follow? All right, if this helps any, here's the equation I gave you a minute ago. I told you that the work done by non-conservative forces is TE final minus TE initial. We will very often use this idea. TE final is TE initial plus the work done by non-conservative forces. And so what Zach said is true. Because we're starting at 0, if you add 519, you're going to end 519. Good? Okay. Ultimately, though, I want you to understand this conceptually. This is the work that Roy did. So that's the work done by non-conservative forces. That's how much energy we gain. So we gain 519.6 joules. Means, what's my total energy over here going to be, you guys? 519.6, right? Ooh, look at that. Okay, so, is everybody good with what I did here? Why the total energy is 519? That's how much work we did, that's how much energy we gained. All right, great. Now, if the height is 0, that means... Tell me something about energy, guys. If the height is 0, GPE is 0. Aha, that means that my KE must be 519.6. And why am I happy now? Because now we can find that velocity, right? All right, so we're almost done. So V equals 2KE over M square root E. And plug in your numbers. What's our mass? 40. Take your square root and you get... Oh, the answer's on the sheet. Yeah, 5.1 meters a second. Make sense, you guys, or no? Any questions? All right. So right now, if you're like me, right now I'm thinking, great, but why the hell would I do it that way? Why wouldn't I just use Newton's second law and do, net force equals mass times acceleration and then use old equations? And to be honest, that's what I would do to solve this problem usually. Okay, because it's easier, right, than going through all this. There's a lot of zeros here and just garbage, right, that didn't affect it. Okay, but sometimes it's way easier to do it using work and or energy. Okay, so I believe that the next example is such an example. So we got kid going down a slide here. All right, so. All right, so let's see if we can read through this example. Oh, actually, this isn't the one I was thinking of. This one actually probably would be just as easy to do either way. The next one is the one I was thinking of. All right, this one is actually pretty similar to the one we just did, but it's got an inclined plane. So, I still think it's easier probably to do it this way than it would be to do it using Newton's laws. All right, so anyway, so we get kid on a slide. The mass is 20 kilograms, so let's draw this thing. So here we go. Here's the slide. Oh. There's the slide. All right, so here's what we know. We know that the mass is 20 kilograms. We know that at the top of the slide, the height is 3 meters. She sits at rest at the top. She slides down the slide, which is 6 meters long. Find her velocity when she gets to the bottom of the slide, 0.75 meters above the ground. So the slide doesn't go all the way down to the ground. And we're trying to find the velocity down here. And it tells you that friction exerts a force of 25 newtons. So as she goes down the slide, we're going to have this force of friction of 25 newtons going up the slide. All right, so solving this using Newton's laws would mean finding your parallel component of gravity. To do that, we need to find our angle. There'd be a bunch of trig here, right? Okay, this solution, no trig. Okay, so yay, right? Those of you that are working on your identities. All right, so before I do anything, is everybody good with what's on the board right here? How I went from text to drawing. All right, cool. So there's a few just sort of knee-jerk reactions that you need to have. If you know your height, find your GPE. If you know your velocity, find your KE. Okay, so let's go through and do all those things, okay? So up here at the top, since the height is 3, if you calculate the GPE, you end up getting 588 joules. Since the velocity is 0, the kinetic energy at the top is going to be 0. So that means my total energy at the top is 588 joules. So that's up here at the top. Pretty good. All right. Now, down at the bottom, I know the height, so I can find my GPE. It turns out to be 147, yeah, 147 joules. But I don't know the velocity, so I can't find the kinetic energy. Cool? Now, up till yesterday, everything we did was frictionless. So if this had been a yesterday problem, we would just go, oh, cool, that's easy though, because I know the total energy is 588, and I can find the kinetic energy and then find the velocity. We'd be done, right? But that's not the case now. Why isn't the total energy constant? Yeah, friction doesn't work, right? So everybody point for me. Which way is the kid going on the slide? Down the slide. Which way is friction going? Up the slide. So our work is going to be negative. She's losing energy as she goes down the slide, right? Follow? So when you get to this step, when you get to like, well, I need the velocity to find the KE, and I need the KE to find the velocity, your question should be, what's going on with the total energy? If it's changing, find your work. And that's exactly what I'm going to do. So, for this problem, work is force times distance, technically times the cosine of 180, right? But I'm just going to, in my head, go, oh, well, the force is this way, the displacement's this way. So my work is going to be negative, right? So the force of friction is 25 newtons. What's my distance? 6 meters, right? Because that's how far she slides while she's going down the slide. And then one of those two things has to be negative, right? Either down is negative or against the motion is negative, but something there is negative. So you end up getting negative 150 joules. Follow? All right, so now you can either, depending on how you like to solve problems, if you're somebody who likes to go by equations, then here's your deal. You're going to go, well, I know my TE initial. I don't know my TE final, but I know my work. So you can do TE final equals TE initial plus the work done by non-conservative forces, right? Which is at 150, right? Negative 150. Okay? If you're like me, you just think about a concept key and you go, well, I started with 588, I lost 150, so down here I'm going to end up with 435. Oh, except it's not newtons.
438.
438? Really? Oh, right. Yes, thank you. Sorry. Sorry about that. Thank you for correcting me. All right. Everybody good with how I got that 438? Again, you can either just subtract or you can use an equation. Either way gets you the same result. Okay, cool. So now what, you guys?
Subtract on GPE.
Just subtract to find your KE, and then you can find your velocity, right? Okay. So if you do that, this KE ends up being 288, which I can now use to find my velocity. And you get 5.4 meters a second. Are these hours gruelingly long when I'm talking this whole hour? It always flies by for me, but from your perspective, it probably sucks, huh? No? Hmm? Okay. Oh, I did not. Happy birthday. For me too. All right, are we good with this? All right, now, all right, before we go on to the next example, I want to tack on a part B here. All right, so look, this is the velocity at the bottom of the slide, right? So she's moving when she gets to the bottom of the slide. Suppose she went blunk and hit the ground. All right, could we find the velocity she has when she hits the ground?
Yeah.
Let's think about what happens. So at this point, let's think about what we know. At that point, let's see, the height is 0, so she's not going to have any GPE, right? The question is, what's her velocity? That's not us, right? We get it at 42, right? Okay. All right, so thoughts? And this is the calculation here is simple, but there's a big concept I want to make sure you guys get. Say it again.
Your last velocity, which is usually from there down.
If you're saying what I think you're saying, yes. Tell me a little more.
Like your H is 0.75, like from the bottom of the slide down.
So you're saying going from here down?
Yeah.
Okay, so what do I... You're right. That there's something important about... There's something very different about the motion down the slide versus the motion after you fall off the slide.
Is there no friction?
There's no friction anymore, right? There's no work. So what is the total energy as she hits the ground, you guys?
This or 438.
Give me a number, you guys. 438, right? Right? Because that's what her total energy is here. Follow? And then she goes flying through the air. There's no friction, so her total energy there is going to be 438 too. And since the GPE is 0, that means that the KE as she hits the ground is 438 joules, which you could then use to find your velocity. Notice, that's a projectile problem, isn't it?
Yes.
And whoa, this is way easier to solve than using components and all that garbage, right? Okay. So anyway, you plug this in, you get 6.6 meters a second. All right, there was a hand up. Yeah, Zach. No, sorry, Parker.
The acceleration doesn't change the kinetic energy because the GP is lowering as she gets lower.
Say that one more time.
So why would your acceleration due to gravity change?
It totally does. The kinetic energy went from 288 to 438.
But that, so that all of her GP turns into K.
Because of the force of gravity. That's why it's a conservative force. All we're doing is we're losing the potential energy we've got stored and converting it to kinetic energy. Make sense? Good, you guys? Any problems? All right, this next example is a great example of where using work and energy is way easier than messing with Newton's laws, okay? So Big Ed pushes a 40-kilogram box up a ramp that's 5 meters long and 3 meters tall. He uses a horizontal force of 700 newtons. Find the velocity of the box when it reaches the top. All right, so let's make ourselves a drawing. Here's the ramp. The problem told us that it's 5 meters long and 3 meters tall. What do you notice about this triangle? So 3, 4, 5 triangle, so that means this side is going to be 4 meters, right? And we're going to push this thing. So notice gravity, and then you've got these stupid components, right? So to find those components, we'd have to find this angle. It gets yucky, right? Ed's force is horizontal, which that's even worse. Like force of Ed, 400 newtons. So if we were to solve this using what we learned when we did forces, you'd have to find the parallel component of this and the perpendicular component of this, and it just gets ugly. All right? So, but check it out. Let's do this. Down at the bottom, tell me some stuff that I know that's important.
GP is 0.
Height is 0, GPE is 0. What else? It doesn't say. We'll assume it pushes it from us. Sorry, that's my bad. Otherwise, there's no way you can solve this if you didn't make that assumption. So kinetic energy is 0, so the total energy at the bottom is 0, right? Okay. Now, up at the top of the ramp, up here, the height is 3 meters, so I can certainly find the GPE. So that would be 3 times 9.8. It gives you 117.6 or no decimal. But we're trying to find the velocity, and so I don't know the kinetic energy.
Isn't it 700?
Oh, it is 700. I'm sorry. Thank you. I'm glad you guys caught that. Thank you. All right. So, is the total energy constant? No. So what should I do? Find the work. So work is force times distance, right? So there's a couple ways you can do this. So remember, work, I don't want that to be in blue. I want it to be in green. How about work equals FB. All right, so what I need to do is either I need to find, so point for me, guys, which way is the distance? It's up, right? The force is this way, right? So they're not parallel. So I got to worry about the angle a little bit, right? Okay. But check it out. I could also do, technically it's FD cosine theta, right? But remember, I told you can do force times distance as long as you pick either the parallel component of the force or the parallel component of the distance. Say it again, Evan. What's 4? The parallel component of my distance is 4 meters. Right? So he's pushing it 700 newtons horizontally, a distance of 4 meters. And you get 2,800 joules. Now, if you wanted to, you could find the angle and you could do FD cosine theta and you'd still get the same answer. So like if I lost you on that little shortcut, that's cool. Find the angle and then do FD cosine theta and you get the same answer. Make sense or no? All right, great. So why do we care about the 2,800 newtons? That means we gained, or sorry, I said newtons. Why do we care about the 2,800 joules? It means we gained 2,800 joules of energy. So the total energy here ought to be 2,800 joules. And so now I can find my kinetic energy, right? And it turns out to be what, 1624?
Yeah.
And now you can find the velocity. No trig. Now, there will be problems where you have to do a little bit of trig, like we did yesterday, like to find the height and that kind of stuff, but hopefully this will keep things a little bit simpler. Cool, you guys? So, there's one more example. I don't think we have time to do it. Let me just say this. at the heart of every one of these problems is these two equations. I guess I should put an NC here. Right? Work done by non-conservative forces is your change in total energy. The work done by non-conservative force is equal to whatever that non-conservative force is times distance, right? Yes, times the cosine of theta. So what's always going to happen is you're going to use one of those two equations to find the work, and then use the other equation to find some unknown thing. This is very similar to when we did torque. We had two equations for torque, right? Fd and I alpha, right? Same idea. So in the same way that these were at the middle of all those torque problems, these are going to be at the middle of all the work problems. Good? That's the last example, the one that I'm not going through right now, is like that. That's definitely on the difficult end of things, and I don't think I put anything like that in the homework. All right. The one nice thing about these work problems, you guys, is I think there's maybe a little less algebra because I have to give you the mass, right? Because how the force affects the mass depends on the mass. Okay? All right, so in the back, you guys picked up some homework assignments. So 8.4a will probably be due on Monday. Okay? Remember, 8.3b is due tomorrow. Okay? 8.3b due tomorrow. Sure. Yeah.